Oh, right. This is one of my favorite calculus problems. And there are a lot of different versions of this that are all essentially the same problem. So pause the video, read the question, go ahead and draw your own picture and think about it. Okay, so what we've got here, let me draw a picture. I've got some lake here, and out here is an island. Let's put it right there. There's the island. And it is 2 miles from the shore. And then over here, north, south, east, west, on the west side, we got a house out here 6 miles away. And we've got this visitor. She's way over here. She's going to walk down the shore. And at some point, let's call it capital P, she's going to start swimming toward the island. So she runs along the shore here, calculates the exact spot along the shore where she can start swimming toward the island to minimize her time. Okay, so where is this used in the real world? Lifeguards. Imagine out here is somebody drowning, and here's the lifeguard. He could run all the way down until he's directly across from the person and then start swimming toward the person. But that's a long distance. Or he could, say, swim the whole way, just jump right in the water and swim the whole way. But he swims slow. He can run faster than he can swim. So there is some magic spot along here where you run as far as you can and then start swimming to minimize the time and get to the person drowning as quickly as possible. Or another example of this is maybe you want to build a pipeline. Maybe you're an oil company and you're trying to build an oil pipeline to get from the refinery to this island. And you don't want to minimize time, you want to minimize cost. And it costs you more money to put pipe underwater than it does along the ground. You want to minimize your total cost. So you're going to run the pipe along the ground for so long and then underwater to minimize the cost. It's the same exact kind of problem. Now, what I find really interesting, imagine you go to the beach with your dog. And so you're over here, you throw the Frisbee out into the water, and your dog is going to run along the beach, and then he's going to jump into the water and swim and get the Frisbee and come back. After 3 or 4 tries, like you keep doing this with your dog will figure out this spot here to get to the Frisbee the fastest. Your dog can solve this calculus problem in his head, just through trial and error. I mean, they're not really doing calculus. Through trial and error, scientists have shown that dogs will find this spot or pretty close to it to minimize the time it takes to get to the Frisbee, because they know that they can run faster than they can swim in the water here. So they'll do it. Like, you think it's so cool. You take your dog to the beach and keep throwing the Frisbee in to the water. They'll find pretty close to this magic spot that minimizes the time. All right, let's do this problem. Okay, so just remember here, we run at 8 miles per hour and we swim at only 3 miles per hour. So we're kind of trying to stay out of the water as long as we can. If we just went the total distance all the way here and only swam 2 miles, that wouldn't necessarily be the best, but that would definitely be better than swimming the entire way. Okay, let's call this distance here x. X is the distance, not the total that we ran, but 6 minus the total that we ran. So the distance that we're running, that distance there, is 6 minus x, because this total distance was 6. Let's call this distance that we're swimming here r. So we're going to run for 6 minus X miles. And we're going to swim for R miles. But what is R? We've got a right triangle here. Just Pythagorean, R would be square root of 4 plus X squared miles. Okay. So there's our setup. We've got a nice, well-drawn, labeled picture. We've defined all of our variables. Let's write here that P is the point where we jump in the water, where we start swimming. And X is the distance, not from the house to P, but from P to perpendicular to the island. That says perpendicular. So at the end, when I say, like, where should we jump in the water? And we try to write out P is blank. We're going to have to think about this. P is 6 minus X miles from the house. Okay, now how are we going to solve this? We're trying to minimize time. So we're going to have to write out time as a function that we can take the derivative of, a function of one variable. Our only variable here is X. By the way, if you're curious, yes, I could have called this distance X, and then this would be 6 minus X, but that would have made R much nastier looking. And I just know from experience that the algebra is easier later if we call this one X. Okay, well, remember distance equals rate times time. We're running at constant speeds. So D equals RT. So time will be distance divided by rate. So our run time, let's call it time run, will be the distance that we're running, 6 minus X, see right there. That's how far I ran, divided by my run speed, 8. And like I'm going to split that up and call that 3/4 minus X over 8. And then swim. How long do we swim for? So let's call that T swim. Will be the distance I swim, square root of 4 plus X squared over the rate, which was 3. So then my total time as a function of X, just add those times together. Okay, what about my domain? What X's make sense here? We always have to think about domain because we have to check our endpoints. What's the biggest X could possibly be? 6. I definitely would not want to run to the left and then start swimming. Like, think about that. If X were 7, then that would mean I start from 7 miles away and swim all this distance. X cannot be bigger than 6. And I definitely wouldn't want a negative X. Right? I definitely would not want to run past the island and then start swimming from this side. So X is between 0 and 6. So we could, right now, if we wanted to, go ahead and find T of 0, literally just plugging a 0 in here. And like, so that's a 0. That's a 0. That is 1.42 hours. I've already calculated it. That's how long the trip would take you. And I could plug in a 6. So literally just plugging in a 6 for all your x's. You could check this on your own, 2.11 hours. So T of 0 would mean you run all the way down the beach, x is 0, and then you swim this 2 miles. T of 6, this other one, that would mean that you just swim the entire way. That's what your time would be. There's going to be a smaller value someplace in the middle. All right, so every single time on these optimization problems, write what you're trying to minimize or maximize as a function of one variable and then take the derivative. So T prime of x here will be right here. I'm going to get -1/8. The derivative of a constant is 0. That's why I split that first part up. Plus, now I got to take the derivative of this guy, derivative of square root of anything. I want to think of that. So square root of 4 plus x squared. Think of that as 4 plus x squared to the 1/2 power. That's not calculus, that's just algebra. Now I'm going to do the calculus. The derivative will be 1/2. That 3 still exists. So there's that 3. That's where that came from. Times leave the inside alone to the -1/2, 1/2 minus 1, and then times the derivative of what's inside, which is 2x. Okay, so some stuff happens here. This 2 and that 2 will cancel. I'm going to get -1/8, and I'm going to end up with x over 3 square root of 4 plus x squared. Okay, check that you see where all the details came from. Negative means put it in the denominator. 1/2 power is a square root. Okay, I want to set this equal to 0. Okay, so we got a little bit of algebra to do here, but we can do this algebra. I'd move that 8, that 1/8 to the other side. And then I'd cross multiply. So 8x will be 3 square root of 4 plus x squared. And then to get rid of that square root, I would square both sides. So 64x squared will be, so I'm going to write this out. Square both sides. 3 squared is 9. Square root of junk squared is just junk. That's a quadratic, and it's actually a pretty easy quadratic. I can use the square root property here. I get 36 plus 9x squared. Move everything over. I think that's 55. X squared equals 36. So x squared is 36 over 55. Take square root of both sides. Remember, x can't be negative. We already established our domain is from 0 to 6. So I don't have to worry about the plus or minus. X will be 6 over square root of 55. So I did square root of top and the bottom. And that's in miles. Okay, so now I'm going to plug that back into the original function. Don't plug that in the derivative. If you, like, you can go through the math if you want. If you plug in that number in here, you're going to get 0 because that's the work we just did. I want the original. So the total time is T of that number. And I've already worked that out. Like, check this on your own. That is approximately, by the way, 0.80904. And when I plug that back in, I get about 1.368 hours. So that is the minimum time. It occurs at this time, it occurs at this location, and that's what the value of it is. And then the point P is 6 minus that, whatever that is, miles from the house. And then I would want to circle all of this. This is in miles. Okay, really good example. I like this problem a lot. Hint, hint.